Greetings of the day. Welcome to the course on Operations Research Technique. In previous lectures, we have studied what is linear programming, and we have arrived up to how to formulate the mathematical relationship from given data. In last lecture, we have seen one problem wherein we have seen basic steps of formulation of linear programming equations required for further solving either by graphical or by simplex method by using the formulated version of the problem. So today we will see more varieties of problems from the point of view of formulation of the problem from given data depending on the conditions given in the problem. We will have recap of the last problem, what we have studied in the last problem, what were the requirements and how we arrived at one particular conclusion, and then we will go ahead by some additional problems. So in our previous lecture, if you recall, we have seen varieties of problem. In that we have discussed this particular problem wherein the objective was to determine the optimal product mix. That was the requirement of this particular problem, and in this problem the word profit was used on per unit of alpha pen produced and beta pen produced. So here directly what to do, that is whether to maximize or minimize, was not mentioned in this particular problem. So in such problem, as an OR specialist, what we have to do is we have to identify, we have to smell the contents of the problem, and based on the contents of the problem we have to decide whether to maximize or whether to minimize given constraint. Now since in this problem the data is pertaining to profit, naturally the objective function related with profit will always be maximize profit. So the examiner or evaluator must have used here the word, it is not compulsion on him that he should give you either maximize or minimize the objective function. As a OR specialist, we should be in a position to identify it. So naturally in this problem objective function will be maximize profit. And now, as discussed in previous lecture, constraints are on resource R1, also on resource R2, and here the maximum availability of these R1 and R2 is stated as 5 and 12 units respectively. So what we have to do is, from this data, from this raw data, we have to first prepare a table. So again I will have some revision of the work which we did in the last lecture. Say alpha is one type of pen and beta is other type of pen for which you need resource R1 and resource R2. And you are having profit per unit of, alpha and beta mentioned as rupees 6 on alpha and rupees 5 on beta. So I have taken these values from the data given. we have to be very careful for the resources R1 and R2 which are given, how these panes are using these resources. So here if you read it carefully, each unit of alpha pane, alpha requires 1 unit of R1, alpha needs 1 unit of R1 and 2 units of R2, alpha needs 2 units of R2. Similarly, each unit of beta requires 1 unit of R1, beta 1 unit of R1, and each unit of beta needs 1 unit of R1 and 2 units of R2. So here we have written in a wrong way. Here it should be 3 units of R2. So here it should be 3. So now it is representing, this summary is representing given for wording problem. Alpha requires 1 unit of R1, 1 unit of R1, 3 units of R2, 3 units of R2. Got it? Similarly, beta requires 1 unit of R1 and 2 units of R2. Now we have to put one additional information in this summary, that availability of this R1 is 5 units. So this is the column of R1. So availability of this is 5 units. Similarly, for R2 availability is 12 units. So this is what we did here, is entire summary. This is in summarized form, the wording data. Now we have seen in the steps that we have to identify decision variable. What is asked in the problem is determine optimal product mix. When it is given determine optimal product mix, so we have to decide number of units to be produced of the pane category alpha and category beta. So to begin with, what we will do is, we will assume let x1 be the units of alpha pane to be produced and x2 be the units of beta pane to be produced. Now how to link this, that I will explain here. Objective function is maximize profit, that we have seen because profit value is given. And we have seen when we write formulation, we start with let x1 and x2 be the number of decision variables of the given parameter in the problem, and it is subjected to a series of constraint, equations pertaining to series of constraint, and last is non-negativity condition that we have seen. Now here, since I have assumed x1 is the amount of alpha pane to be produced, and we have also seen, if you recall, assumptions in linear programming problem as proportionality, additivity, certainty, continuity. So now in formulation we will use all these assumptions to formulate the given problem from the wording data. So here we go like this. On 1 unit of alpha pane, profit is 6. Suppose I am manufacturing x1 units, so profit will be, it is multiplication of these two, 6x1. Similarly, for beta, profit will be like this, 5x2. This is objective function. So I can write now maximize z equal to 6x1 plus 5x2. Maximize z equal to 6x1 plus 5x2. Now this is subjected to two constraints. Constraints are on resource R1 and resource R2. we have seen how to use the signs like this, or equal to. First one is, this is less than equal to sign, this is greater than equal to sign, and last one is equal to sign. We have seen the situation in which we have to use particular sign. So we have stated many a times, when it is maximum availability or not more than wording, our sign will be less than equal to. Our sign will be less than equal to. In this particular case, it is given that each unit of beta, it is given that manufacturer has 5 units of R1 and 12 units of R2. It means that he is not having more than 5 units of R1 and more than 12 units of R2. Maximum availability of R1 and R2 is 5 and 12 units respectively. So the sign for this constraint will be less than equal to. And how will be left hand side of the constraint? We will see that this R1 is needed for both alpha and beta pane. So here what we have to do is, we have to multiply, cross multiply this like this, cross multiply like this. So it is given for 1 unit of alpha you need 1 unit of R1, you are producing x1 unit. So proportionality condition for alpha pane, for 1 unit you need 1 unit of R1, for x1 unit you will need x1 into 1, that is x1 R1, x1, here also x2. So the equation will become now here 1 into x1 is x1, 1 into x2 is x2. So x1 plus x2, maximum availability is 5, x1 plus x2 less than equal to 5. Similarly for R2, it will be multiplication of x1 with, for R2 it will be multiplication of x1 with R2, that is 3, and x2 with R2. So here if I cross multiply, for R2 it will be 3 times x1 plus 2 times x2 less than equal to maximum availability 12. So in nutshell, what we will get here is one objective function, 2 constraints of R1 and R2, and 1 non-negativity condition. So here I have given this in final version and it speaks like this. First, decision variables. So assumption, let x1 and x2 be the number of beta panes respectively. Linear programming model, for that we have discussed that maximize total profit. This is z equal to 5x1 plus 6x2. These are subjected to constraints. One constraint is for R1, other constraint is for R2, and last is very important condition, non-negativity condition. Now here it is not mandatory that in bracket you must write this constraint. It is not mandatory, but for understanding point of view, even if we write that these equations belongs to this constraint, there is no harm. So this is the entire process of formulation of the problem. Now we will see other problem, other wording, change of wording, and how we can formulate the problem from that particular example. So here again, if you recall my deliberations on application of LPP in real life, so one of the application I have mentioned was related to diet problem, and in diet problem for individual we should have sufficient quantity of minerals, vitamins and all related parameter for healthy life. So this particular problem speaks of the contents with conditions given in the problem, and based on that we have to formulate first the problem, and then after formulation further step is finding the values of the decision variable which you have assumed. So if you read this problem carefully, here some data is given in now other form with other wordings like that. Here he has used at least. A diet for sick person must contain at least. So the condition he is quoting, and we have seen whenever there is at least, which sign we have to use. Similarly, this at least condition is for vitamins, also for minerals and also for calories. So that person need this much minimum quantity in his diet of vitamins, of minerals and of calories to improve, being sick person. He is the sick person. Two foods A and B are available at a cost of rupees 4 and rupees 3 per unit. Now here in last problem it was given as profit, here it is given as cost. Two foods A and B are available at a cost of rupees 4 and 3. 1 unit of food A contains, this is important, 1 unit of food A contains 200 units of vitamins and 1 unit of mineral and 40 calories. Similarly, 1 unit of feed B contains this much amount of vitamin, this much amount of minerals and this much calories. What is asked? Formulate, see here, formulate this problem as an LP model, linear programming model, that is asked, and solve it. We'll see there are so many methods to solve. He has mentioned solve is by graphical method. To find combination of foods to be used to have a least cost. Now in this problem the objective function is stated that cost of that complete diet has to be least, that is minimum. So objective function is well defined over here, that you have to work out for minimization of cost. So objective function is clear, and now we have to decide that these foods A and B of which costs are given, how much to produce so as to improve the health of sick person. So again, in summarized form we have to write the data. In summarized form we have to write the data, and based on that we can then find the values of further values of quantities of food A and B. So like in previous problem, here also we'll start with let, what is asked here, combination of foods to be used, and here he is talking in the terms of units, like per unit. He has given per unit. Here also he has mentioned the amount as units. So to begin with, I have some work with, say, suppose like in previous case we have alpha and beta pain. Here we are having alpha, A food and B food, A food and B food with 3 ingredients in that. Ingredients are vitamin, other is minerals, third is calories. So assume x1 is the number of units of food A, x2 as number of units of food B. Cost associated with A is given as 4, cost associated with B is given as 3. So my objective function for this problem is decided. It will be minimize Z or minimize in bracket total cost Z is equal to 4x1 plus 3x2. 4x1 plus 3x2. Now there are conditions posed on this availability of vitamins. Vitamin total availability is 4000, minerals is 50, and calories here we should write cost calories, here cost as 4 and 3. So calories total amount is 1400. But the condition used is at least. Now he has given that this vitamin is also used by both the products A and B. So here he has given 1 unit of food A contains 200 units of vitamin A, 200 units of vitamin, 1 unit of mineral, 1 unit of mineral, and 40 calories. 40 calories. This is contents for food A. Similarly, he has given for food B. Food B, the contents are like this: 100 units of vitamin, 2 units of, here I will change the marking. Here he has given 100 units of vitamin, 2 units of mineral, and again calories is same in both cases. So this is the summary of this wording data for linear programming formulation. No item is missed in this particular summary table from the given data. And now we have to be very cautious for this particular word used in the problem, that at least the diet plan must have minimum 4000 units of vitamins, 50 units of minerals, and 1400 calories. This condition is specified, but with at least means minimum should be given quantity either 4000, 50 or 1400. Greater than these values is welcome situation, but it is not permitted that this value will be less than given value, since the condition is at least. So here in this problem for formulation, very important, we have to use the sign greater than equal to, since the condition is at least. So how we can then formulate, how we can write end version of linear program is like this: for objective function minimize Z, 4x1 plus 3x2, 4x1 plus 3x2, subjected to constraints. Now here we will have 3 constraint equation: one constraint equation for vitamin, one constraint equation for mineral, and other for calories. Constraint equation, but with conditional sign, it will be greater than equal to, quantity of resources available will be greater than equal to. So how we will go? 200 x1 plus 100 x2 greater than equal to at least sign, greater than equal to 4000. Similarly, x1 plus 2x2 again greater than equal to 50, at least sign. Third, 40x1 plus 40x2 greater than equal to 1400 because of at least sign. So must have understood the impact of this word at least in formulation. He can also use other term, minimum. Minimum diet must contain minimum quantities of. Minimum is also equivalent to at least. If it is not more than wording, we have to use the sign less than equal to. Clear? So 3 equations and followed by one last equation, that is non-negativity condition, which is very essential. So that is x1 plus x1 comma x2 greater than equal to 0. So we'll check out how exactly the formulated version looks. See here, this is summary table that we have just formulated and explained. We did in our own, and this is final linear program from the given data. Objective function minimize, 3 constant equation, one for vitamin, other for mineral, third for calories, with important sign, this sign, this sign, and this sign greater than equal to. This is non-negativity condition. Always you have to end your formulation for any linear programming problem. Remember one thing in mind, it won't be given in the problem, negativity condition. After writing your conditions, constraint equation, you have to put this last non-negativity condition in the form of equation, that decision variables which you have assumed are greater than equal to 0. Next problem. So this is the problem wherein in first problem we have studied how to tackle when the objective function is maximized. With constraint, all constraints in that problem were less than equal to type. In second problem, what we have studied? Objective function was minimized and the signings, logical signings for all constraint equation were of the pattern greater than equal to type. Now we'll see third problem and we'll see as per given condition what should be the logical signs to be used for linear program formulation. So this is third problem. First what we are doing is we are practicing how to formulate the mathematical equations from the given data. Once we are through with formulation, then it is easy to solve those formulated version by stated method. Remember, if formulation is wrong, entire efforts taken to solve those problems will be wrong because your foundation itself is wrong. So ensure that your formulation must be precise and correct as per given condition. Now in this problem, you can see here You can see here the standard weight of special purpose brick is 5 kg and it contains two basic ingredients. One is standard weight, basic ingredients B1 and B2. B1 cost rupees 5 per kg, B2 cost rupees 8 per kg. This is the data given. Strength of brick required dictate that brick should contain not more than 4 kgs of B1 and minimum 2 kgs of B2. Since demand for the product is likely to be related to the price of the brick, graphically find out minimum cost of the brick satisfying above conditions, means these status conditions. Again in this problem, suppose even if this is not given, that minimum cost parameter is not given, and if it would have been the simple problem that determine optimal mix of the ingredients, we should smell out that the objective function must be, in this particular case, is minimize cost, because cost is given. Now how this problem is different from earlier problem is, here you can find the word, first is not more than, and second is minimum. Conditions pertaining to quantities of ingredients to be used in that brick. Brick is made up of two ingredients, ingredient B1 and ingredient B2. And here, very important, standard weight. The brick which we are making from using ingredient B1 and B2, its weight of that brick must be 5 kg. It cannot be greater than 5 kg because the word used is standard. It cannot be less than 5 kg. So now this is very important problem wherein you will be coming across all three signs. We know when it is implied condition, must or standard like that, we have seen in our earlier lecture that here the sign to be used is equal to. Second, when it is not more than implied condition, maximum, not more than is maximum, the sign will be using here will be, for this case, will be less than equal to type. Getting it? And here, for such condition, the sign used will be minimum, so it will be greater than equal to. So this is the problem wherein we come across all three types of signs. So now we know how to proceed. Usually we start with let x1 be the kgs of ingredient. We have to decide, we have to have two ingredients B1 and B2, of which we are assuming with let x1 and for x2. Clear? Cost is given. Cost for B1 per kg is mentioned as 5 and cost for B2 per kg is mentioned at 8. So my objective function is ready. It is 5x1 plus 8x2. Now these B1 and B2 are used in limited quantity. So from this, objective function will be definitely minimize Z. It would be 5x1 plus 8x2. 5x1 plus 8x2. Now this is very important, further part. Subject to see here, standard weight of special purpose brick is 5 kg and the brick is made up of two constituents B1 and B2, of which we are assuming x1 and x2. So for this first, it will be x1 plus x2 standard weight, therefore the condition will be 5. First equation will be for this sentence. Clear? Second, it is given strength consideration dictate that brick should not contain more than 4 kgs of B1. B1 you are assuming by B1 you are correlating with x1, B2 you have correlated with x2. So x1 not more than 4. When it is not more than 4, I have to use sign less than type. Clear? Similarly, x2 minimum 2. B2 is x2 minimum 2, and last is x1 x2 greater than equal to 0. So this particular equation consists of, this is one pertaining to equal to sign, second pertaining to less than equal to sign, and third describing use of greater than equal to sign. So now you will see final version of the same. See here, this is the way we have written after making that summary table. So if you want to write in a final form to be represented to your boss, to higher ups, it has to be like this. Decision variable x1 x2 be the basic ingredients, LP model, minimize cost, two constraints with, again important, constraints with this is first equal to sign, less than equal to sign, and greater than equal to sign. So this is how in real life, based on the given condition, we have to formulate the problem. Again we will see one problem, last problem related to formulation, and once we get mastery over formulation of the problem, we will switch over to further part, that we have started with what is LP, we have defined OR, then we have defined linear programming, we have studied basic assumptions, requirements, and then steps of formulation of linear programming problem from the given wording. And now we are towards the end of formulation of the problem from the given data. So sufficient practice we did to understand what are the contents given in the problem, and based on their signs, that is less than equal to, greater than equal to, how to put those logical signs in the form of equation with assumption that let some decision variables be there. Now here, read this problem carefully to understand again. Now here it reads that Amruta Electronic Company produces two products, P1 and P2. So production of two products, instead of giving name to the product, it is stated as product P1, product P2. Products are produced and sold on weekly basis. The weekly production cannot exceed for product P1 by amount 25 units, and for product P2 35. This is very important. Cannot exceed condition is given because of limited available facility. Why production cannot exceed? Because that organization is having shortfall of the facilities needed to produce those P1 and P2. The company employs total of 60 workers. Maximum workers with the organization is 60. Product P1 requires 2 man weeks of labor, while P2 requires 1 man week of labor. And total profit margin on P1 is 60, P2 is 40. Now here in this problem, nothing is mentioned regarding again your objective function that formulate for such and such thing is not mentioned. We have to smell out the problem, and based on given data we have to identify what will be the objective function, whether it is minimization or maximization, and if it is maximization of which particular parameter. So if we read it carefully, values of profit on P1 and P2 is given 60 and 40 like that. So obviously objective function is now, it's very clear that it will maximize, we write in bracket total profit, that would be objective function. And now since it is asked to formulate this problem as an LP problem, and company wants to decide two products, P1 and P2. So in such cases, we have seen whenever we want to take decision regarding how much to produce, we assume things, and we assume things like let x1 and let x2 be the amounts of, let x1 and x2 be the amounts of units of product P1 and product P2 to be produced. If I am ready with the amounts of product P1 and product P2 to be produced, and if I am given values of related products, profit values are given, so we know that maximized total profit would become then like for P1 is 60, I can write here 60 into number of units of P1 product plus, that is additivity property, 40 per unit profit into number of units of the product P2. So this will be our objective function in this particular case. Now this objective function, now what we did here, being fourth problem, we are trying to solve it from the given data without going to summary table. No doubt you have to avoid mistakes, prepare summary table first and then only jump to the final version of the formulation. If, again I am repeating, if you commit mistake in formulation, you will be totally wrong in your solution, whether you find it by graphical method or by analytical method. Those methods will be studying in coming lectures, but the prerequisite for graphical solution or analytical solution is correct mathematical formulation of the problem. Now this is objective function as far as this problem is concerned. Conditions are given, cannot exceed amount of resources for this and limit number of workers. So 60 workers, total company employs total 60 workers. It means that is the maximum availability of workers available with the company. It cannot be 61. At the most it can be 60 or less than 60. It may be 10, it may be 20, it may be 59, it may be 60, it cannot be 61. So for that we have to use sign less than equal to. Now if you go for that, based on the constraints of previous problem which are given, the final version of formulation will be like this: maximize Z 60 x1 60 units of P1 to be produced, 40 units of P2 to be produced. This was the condition. The sign was minimum, and therefore we could see the word here less than equal to 25, here less than equal to 35, and here equal to 60, because total number of workers required for that production of P1 and P2 required in the problem is 60 hours. So this is the way how in real life you have to solve the problem. And further part of this particular series is, after linear programming formulation, is finding solution. And there are methods for finding solutions to given linear programming problem. It is either graphical or simplex method. So today we will stop our lecture at this note that we have finished formulation of given problem, and from next lecture we will study how to find solution of a given problem with the help of graphical method.